Noche Cósmica.
The light you see when you glance up at the night sky has been traveling toward you for so long that it left its source before humans learned to write. Some of that light, the faintest smudges visible only through telescopes, began its journey when our species was still learning to farm. And yet, by the time those ancient photons reached the observatory domes of the early 20th century, the galaxies that sent them were already impossibly far away, still rushing outward into the dark. They were fleeing, not from something, but into expansion itself. This is the quiet mystery that has occupied astronomers and physicists for barely more than 100 years, though the universe has been answering the question for roughly 14 billion. Why does the cosmos keep stretching? Why is there no center to its growth, no edge that we can point to and say, there, that is where creation ends? The answer to these questions will require us to journey backward through time, to sit with careful observers in cold observatories, to follow the logic of light bending around massive objects, and to contemplate a universe so strange that even its architect seemed reluctant to accept it. If you find yourself drawn to these slow explorations of cosmic mysteries, the kind of patient thinking that doesn't rush toward certainty, but instead dwells in the profound strangeness of how reality actually works, consider subscribing for more evenings spent contemplating the universe's quietest truths. Let us begin where all starlight begins, at the surface of a distant sun, millions upon millions of years ago. Imagine a single photon of light, released from the fusion reactions burning in some star's core. It begins as pure energy, born from hydrogen fusing into helium, and it carries with it the signature of that stellar furnace, particular wavelengths, particular colors embedded in its structure. The photon sets out across empty space, traveling at the speed of light, which is the only speed light knows. Around it, galaxies spin, massive clouds of gas collapse into new stars, civilizations rise and fall on planets circling other suns, and still the photon travels, undisturbed, unchanging, carrying the same information it has carried since its release. This same photon, or one like it among countless trillions, eventually encounters the dome of an observatory on Earth. It passes through glass or reflective metal. It strikes a photographic plate or a sensitive electronic detector, and for the first time since leaving its source, its journey is interrupted. Someone, somewhere, peers at the record of its arrival and asks a simple question: where did this light come from, and what can it tell us about the universe that sent it? What makes this question so profound is that the answer is not what anyone expected. In the early years of the 20th century, before this mystery had even fully taken shape, the night sky appeared orderly and eternal. The stars seemed fixed in their positions relative to one another. The great nebulae, fuzzy patches of light that appeared through telescopes, were thought by many astronomers to be small clouds of gas somewhere within our own galaxy, the Milky Way. The universe, for all practical purposes, seemed to be one great cosmic city, unchanging, static, a realm of divine perfection where nothing essential ever altered. The Earth sat at the center of the celestial sphere, and nothing was peculiar about that arrangement, or so the prevailing wisdom suggested. But light carries secrets, and when astronomers began to examine that light more closely, not merely where it came from, but how its wavelengths had shifted during its journey, they discovered something that contradicted everything they thought they understood. The light from distant nebulae had been stretched. Its waves had been lengthened, shifted toward the red end of the spectrum, and this shift was not random. It appeared in a pattern. The farther away a nebula was, the more dramatically its light had been stretched. There are few moments in scientific history when a single observation quietly demolishes an entire worldview. This was one of them. The realization crept in slowly, like dawn itself. It began with patient observers in observatories, studying photographic plates under dim light, measuring wavelengths with the precision that astronomy demands. These were not people searching for a dynamic universe. They were measuring details in the language of light, and the light was telling a story they had not asked to hear. The universe was not stable. It was not eternal and unchanging. It was moving. It was stretching. Think for a moment about what that means. Not that galaxies are moving through space in one direction or another. That would have been comprehensible, even if surprising. What was being revealed was far stranger. Space itself was expanding. The very fabric of reality was growing larger, and it had been doing so continuously, invisibly, for longer than human civilization had existed. The galaxies were not fleeing through a static universe. They were being carried away from one another by the expansion of space itself, the way two dots drawn on the surface of a balloon move farther apart as the balloon inflates, not because they are moving across the balloon's surface, but because the surface itself is growing. And so we find ourselves at the threshold of a mystery that is still not fully resolved, even now. The universe expands, but why? What drives this expansion? What is the nature of the emptiness between galaxies, the space itself that stretches endlessly outward? These are not questions with simple answers. They are questions that have occupied some of the finest minds in human history, and they continue to guide our understanding of reality itself. As we prepare to follow those careful observers into their observatories, to trace the logic of their measurements and discoveries, the night sky above you in this moment contains within it the entire story of this expansion. The starlight reaching your eyes right now has been traveling across an expanding universe. It has been stretched and shifted by distances so vast that the human mind struggles to hold them. And yet it arrives, gentle and subtle, the same as it has for eons, carrying within it a message that took humanity thousands of years to learn how to read. And here lies a question that has occupied human minds for only the briefest moment in cosmic time, yet one that reshapes everything we thought we knew about the nature of existence itself. The universe, this vast container of billions upon billions of galaxies, each containing billions upon billions of stars, is not static. It is not frozen in some eternal arrangement. It moves, it stretches, it expands outward in all directions at once, and has been doing so since the very first instant of creation. This revelation, which came only within the last 100 years or so, represents one of the most profound reversals in human understanding that science has ever experienced. And the story of how we came to know it, the slow, patient work of astronomers squinting through telescopes and measuring tiny shifts in starlight, is itself a kind of meditation on how we come to understand the world around us. If you find yourself drawn to these quiet, unfolding mysteries of the cosmos, to the slow accumulation of small observations that eventually reshape our entire conception of reality, consider subscribing to this series. Each episode takes us deeper into the universe's most intimate secrets, the moments when human curiosity meets the vast silence of space, moments meant to be savored slowly, gently, as you drift toward sleep. The story begins not with the universe itself, but with human certainty. For nearly all of recorded history, the cosmos seemed perfectly obvious. The stars hung like jewels on a dark dome above the earth. They did not move relative to one another, or so it appeared to anyone watching the night sky year after year, generation after generation. The sun rose in the east and set in the west, day after day, an endless repetition, so regular and predictable that it seemed like the natural order of things, the way things simply were and always would be. And below those perfect, eternal stars lay the earth, solid and stable, the center around which all heavenly bodies revolved. This was not merely a scientific belief. It was woven into theology, into philosophy, into the very fabric of how people understood their place in the grand scheme of existence. To suggest otherwise would have seemed not just wrong, but almost offensive, a kind of cosmic presumption. But then, very slowly, over centuries, observations began to accumulate. Telescopes were invented. Careful measurements were taken. Patterns emerged that could not quite be explained if everything truly revolved around the Earth. And gradually, almost reluctantly, the model of the cosmos shifted. The sun moved to the center. The Earth became merely one planet among others, orbiting in the darkness. And yet, even with this new arrangement, there was still an assumption that held firm. Beyond our solar system, the universe was eternal and unchanging. The stars, which we now knew were suns just like ours, existed in perfect arrangement in space. They might be vast distances away, but they were where they had always been, where they would always be. The universe itself was static, fixed, permanent. This assumption lasted right up until the beginning of the 20th century, when something remarkable began to happen in a small handful of observatories around the world. Astronomers, working with increasingly sophisticated instruments, began to notice peculiar features in the light coming from faint nebulae. These nebulae had long puzzled scientists. Were they clouds of gas within our own Milky Way galaxy? Or were they something else entirely, separate collections of stars existing at distances almost too vast to comprehend? And then the observations began to reveal a pattern, a subtle but unmistakable shift in the light itself. This shift would become the first hint that the universe was not static at all. It was restless, it was moving, and it would take decades of careful, patient work and not a little bit of scientific controversy to understand what that movement truly meant. The quiet work of observation, the slow accumulation of data from photographic plates and spectrographic measurements, would gradually unveil a cosmos far stranger and more dynamic than anyone had imagined. A universe that was not a fixed stage upon which stars and galaxies existed eternally, but something alive, something expanding, something engaged in a process of continuous transformation from the very moment of its creation. To understand how we came to know that the universe was expanding, we need to step back in time to the early 1900s, when astronomy was a very different kind of pursuit. The night sky was not conquered by satellites or computerized surveys. It was discovered slowly, methodically, by patient observers who would spend entire nights in cold observatories, guiding telescopes by hand, waiting for clear skies that might come only a handful of times each month. Imagine the Lowell Observatory in Flagstaff, Arizona, or the Yerkes Observatory near Chicago, where astronomers wrapped in wool blankets would position themselves at the eyepieces of great refractors, their breath misting in the frigid darkness. They were not looking for what they expected to find. They were simply looking, night after night, letting the universe reveal itself in whatever scattered light reached them across the immense distances of space. But there was something transformative happening in those observatories in the early 20th century. Photography was becoming the astronomer's most powerful tool. Rather than relying solely on what a human eye could perceive in a single night, astronomers began attaching sensitive photographic plates to the backs of their telescopes. These plates, coated with light-sensitive emulsions, could gather photons over the course of hours, accumulating signals far too faint for the eye to perceive directly. The universe, in a sense, was writing its own portrait on these plates. What emerged from the chemical baths where the plates were developed were faint smudges of light. Some were stars, recognizable as point sources, but others were much more mysterious. There were fuzzy, nebulous patches that seemed to have some structure, some form. Astronomers debated their nature with genuine uncertainty. Were these merely clouds of glowing gas within our own Milky Way? Or were they something far more distant and significant? The question hung in the darkness of those observatories like a riddle waiting for its answer. The photographic plates accumulated in the archives, thousands of them, each one a fragment of data, a small piece of the cosmic puzzle. The plates were stored carefully, catalogued with handwritten notes, their emulsions slowly fading over decades. In those repositories of imagery were hints of something profound, but the hints were mute, waiting for someone with the tools and the insight to ask them the right questions. Consider what it must have felt like to be an astronomer in those years of early photography. You were working at the very edge of human perception, trying to wring meaning from barely perceptible traces of light. There was no instant feedback, no computer algorithm analyzing your data in real time. You had to be patient with the process, patient with the universe's reluctance to surrender its secrets. You had to believe that the tedious work of gathering data, night after night, was worth the effort. The observatories themselves became temples of a sort. The great domes that housed the telescopes were architectural statements of seriousness and purpose. You did not wander into an observatory casually. You entered it with reverence, understanding that you were engaging in a kind of sacred act, an attempt to understand the cosmos through patient observation. The work was solitary. The work was slow. The work was humbling. Yet within those quiet observatories, within the patient accumulation of photographic plates and careful measurements, the seeds of a revolution were being sown. Astronomers were developing more precise ways of analyzing the light that reached them. They were learning to interpret subtle variations in color, in intensity, in the way light was distributed across those faint smudges on the photographic plates. The precision itself was remarkable. An astronomer might measure the position of a galaxy to within a fraction of an arc-second, a unit of angular distance so small that the human eye could never perceive it. These measurements required not just good telescopes but remarkable skill, patience, and care. There was a craft to it, a tradition of observational astronomy that stretched back centuries but was now entering a new phase, armed with photographic evidence and increasingly sophisticated methods of analysis. Think about what those photographs meant. They were not merely images, they were data. They were a way of capturing the universe in a form that could be studied, measured, compared. The photographic plate was perhaps the first major technological leap forward in allowing humans to see, not just with their eyes, but with machines that could see farther, see fainter, see for longer than any human could. And in those faint smudges on those carefully preserved plates lay the first hints that the universe was far vaster than anyone had imagined, and that it held secrets about its own motion, its own growth, its own fate. The discoveries were not yet apparent, but the data was there, waiting. The observatories hummed with quiet purpose. The night sky continued to pour its ancient light onto the patient instruments below, and slowly, inevitably, the picture was beginning to take shape. In the years before Hubble would become a name synonymous with cosmic discovery, there was another astronomer working quietly in the American Southwest, a man whose careful observations would plant the first seeds of a revolutionary idea. His name was Vesto Melvin Slipher, and he worked at the Lowell Observatory in Flagstaff, Arizona, where the thin mountain air offered some of the clearest views of the night sky available in that era. Slipher was not looking to overturn our understanding of the universe. He was simply doing what astronomers of his time did, examining these faint smudges of light called nebulae, cataloguing their properties, trying to understand what they were. The tool that Slipher wielded with particular skill was the spectroscope, an instrument that splits light into its component colors, much as a prism separates white light into a rainbow. When he pointed this device at distant nebulae and recorded their light on photographic plates, something curious began to reveal itself in the patterns before him. The characteristic lines of light, the fingerprints of chemical elements like hydrogen and helium, were not quite where they ought to be. They had shifted. They had moved toward the red end of the spectrum, stretched and lengthened, as if the light itself had been pulled and distorted by some invisible force. This phenomenon was not entirely unknown. Physicists had already grasped the Doppler effect, that familiar principle which explains why a siren's pitch drops as an ambulance moves away from you. Sound waves compress when a source moves toward you, creating higher frequencies, and stretch when it moves away, creating lower frequencies. Light behaves in a remarkably similar way, though the visual consequence is a shift in color rather than pitch. Light from an object moving away from us gets stretched, shifted toward the red end of the spectrum, what astronomers call a redshift. Light from something approaching us gets compressed, shifted toward the blue, a blue shift. As Slipher continued his patient work through the 1910s, measuring the positions of these spectral lines in nebula after nebula, a pattern began to emerge from his data. The overwhelming majority of the nebulae he examined showed redshifts. They were moving away from us, not just one or two, not scattered anomalies, but nearly all of them. Some were retreating at velocities that seemed almost incomprehensible to the minds of that time, speeds of hundreds of thousands of miles per hour. Here was a quiet observation, born from careful measurement and photographic evidence, that suggested something was fundamentally wrong with the static, unchanging universe that astronomers had long assumed. Consider for a moment what this must have meant. For centuries, the cosmos had been imagined as essentially fixed and eternal, a realm of perfect stability where the stars and nebulae occupied their appointed places like furniture in a room. Yet Slipher's spectroscope was whispering a different story. It was suggesting that these nebulae were not stationary, not locked in their positions, but rather fleeing from us, moving outward into the void. What could explain such a phenomenon? Why would so many distant objects be rushing away? Was the Milky Way somehow repelling them? Or was something more profound occurring, something that involved the very fabric of space itself? Slipher presented his findings to the astronomical community with appropriate caution. He had data, clear data, recorded on plates, measured with precision, but the implications remained uncertain. The nature of these nebulae themselves was still hotly debated. Were they clouds of gas within our own galaxy, nearby and relatively modest in scale? Or were they island universes, separate systems of stars far beyond our own Milky Way? Without knowing what these objects actually were, it was difficult to interpret what their motion truly signified. Without knowing their distances, it was impossible to know whether they were genuinely fleeing or merely approaching from some other direction. And so Slipher's redshifts remained a fascinating puzzle, a peculiarity noted in the literature, but not yet a revolution. The astronomical world was not quite ready to hear what the data was trying to say. There needed to be another piece, another confirmation, another observer, with different tools and a different approach. There needed to be someone who could establish firmly what these nebulae actually were and how far away they truly lay. That someone was already at work in California, on the slopes of Mount Wilson, carefully measuring the distances to stars in these same nebulae, methodically building the first true map of a cosmos far larger than anyone had imagined. But Slipher's contribution, though quiet and easily overlooked in the shadow of what would come next, was essential. He had shown the universe's first clear sign of motion. He had glimpsed, in the shifted light from distant nebulae, the first hints that the cosmos itself was restless, dynamic, and far stranger than tradition had suggested. In the gentle slide of those spectral lines toward the red, the expanding universe was already trying to announce itself to anyone patient enough to listen. Up on Mount Wilson, high above the Los Angeles basin where the city lights pooled far below like embers of a sleeping fire, there stood the 100-inch Hooker telescope. It was, at that moment in the mid-1920s, the largest telescope in the world, and on many clear nights, a patient astronomer named Edwin Hubble would climb the observing cage, settle himself before the eyepiece or the camera plate, and spend hours measuring the distances to nebulae. Those faint, distant smudges of light that Slipher had already shown were rushing away from us. But Hubble carried an advantage that earlier observers did not. Within those same galaxies, he could identify a particular type of variable star, stars that pulse and brighten and dim again in a rhythm as steady and reliable as a heartbeat. These were called Cepheid variables, and decades earlier, astronomers had discovered something remarkable about them. The brightness of a Cepheid, its true luminosity, was linked directly to the period of its pulsing. Measure how fast it brightens and dims, and you could calculate how truly brilliant it actually was. Then, compare that true brightness to how bright it appeared from Earth, and suddenly you could calculate the distance, not by guess or by spiral pattern, but by genuine measurement, by mathematics. Hubble used this method night after night, galaxy after galaxy. He would identify a Cepheid in some distant nebula, photograph it repeatedly, plot its variations, work through the calculations. And each time he did this work, he pulled another nebula out of the cosmic fog and placed it, definitively, at a measured distance. The Andromeda Nebula was not a cloud of gas at the edge of our own galaxy, as many had believed. It was a separate island of stars, far, far beyond the Milky Way, over 1 million light-years away. Beyond that lay others, and others still. As he accumulated these measurements, a curious pattern began to emerge from the data. It was not something that screamed from the numbers immediately, but slowly, as he plotted galaxy after galaxy, distance after distance, the picture came into focus. The farther away a galaxy was, the faster it was moving away from us. It was not random, it was not chaotic, it was proportional, systematic, elegant. Think of it this way. If you measured a nearby galaxy and found it receding at 1,000 kilometers per second, then a galaxy twice as distant was receding at roughly 2,000 kilometers per second. 3 times the distance meant 3 times the speed. The pattern held across the cosmos, galaxy after galaxy, like a vast and orderly choreography. Hubble was not seeing random motions. He was seeing the fingerprint of something much larger, something that affected every galaxy equally, everywhere at once. This was not a motion through space. This was something else entirely. The space itself, the vast 3-dimensional stage on which galaxies sat like spaced notes on an infinite staff, that space was changing, growing, stretching. What Hubble had discovered, though the full weight of its meaning would take time to sink into the astronomical community, was direct observational proof that the universe was not standing still. It was not eternal and unchanging, as philosophers and theologians had long assumed. It was dynamic. It was alive, in a sense. It was doing something. On those quiet nights at Mount Wilson, with the great telescope pointed toward the abyss, Hubble was not merely observing the cosmos. He was watching it unfold. He was witnessing, in those patient measurements and those careful calculations, the fundamental rhythm of creation itself. Each redshift, each measurement of distance, each data point he logged was another thread in a vast tapestry that would soon remake humanity's understanding of where we are and what we are part of. The implications would reshape cosmology, but for now, up on that mountain in the cool night air, there was only the work, the measurement, the pattern, the quiet revelation that the universe, in all its vastness, was telling us something we had never truly understood before. It was telling us that it was changing, always becoming something new. What Hubble discovered, in those patient nights of measurement and calculation, was something almost too simple to be true. Galaxy after galaxy, Distance after distance, velocity after velocity. And with each addition to his growing catalogue, a pattern emerged so clean, so undeniable, that it seemed to whisper a fundamental truth about the cosmos itself. The pattern was this: the farther away a galaxy lay, the faster it was moving away from us. Not randomly, not chaotically, but proportionally, directly proportional. Double the distance, and you would find the galaxy receding at double the speed. Triple the distance, triple the velocity. It was as though the universe had written its own equation into the very fabric of reality, waiting for someone patient enough to read it. We call this relationship Hubble's law, and it remains one of the most elegant statements we have ever made about the large-scale behavior of creation. The mathematics is beautifully simple. Velocity equals a constant, we call it the Hubble constant, multiplied by distance. Just that, a straight line when you plot the measurements on a graph. Distance on one axis, velocity on the other, and there it is, the expanding universe, written out in pure geometry. But what did this relationship actually mean? That was the question that hung in the air, both in Hubble's mind and in the minds of the astronomers who read his papers, with a mixture of fascination and uncertainty. If galaxies were all rushing away from us, did that mean the Milky Way occupied some special place at the center of everything? Were we, somehow, the pivot point around which all other galaxies wheeled? The answer, it turned out, was no. And this is where the universe reveals its true generosity to human understanding. From any other galaxy in the cosmos, an observer would see the exact same pattern. From their vantage point, all other galaxies would appear to be receding, with the same proportional relationship between distance and velocity. It was not that we were special. It was that space itself was the actor in this grand drama, not any particular place within it. The universe, in other words, was not flying apart. Rather, it was stretching, expanding. The very scaffold upon which galaxies hung, the fabric of space itself, was growing larger. The galaxies were not so much rushing through space, as space was unfolding between them, carrying them apart, like a rising dough carries the raisins embedded within its structure farther and farther from one another. This was a profound realization, and it arrived almost unannounced, without fanfare. Hubble had not set out to overturn the entire conception of the cosmos. He had simply pointed his telescope, taken his photographs, measured the light, performed his calculations, and in doing so, he had revealed that the universe was not eternal, static, and unchanging, the consensus view that had held sway for centuries. It was dynamic, it was evolving, it was, in some deep and essential way, alive with transformation. The implications unfolded slowly across the astronomical community. If the universe is expanding now, then logically, reasoning backwards through time, it must have been smaller in the past, denser, hotter, compressed. And if you followed that chain of thought all the way back, past billions of years, past millions of years, you arrived at a moment, a singular point in time, where all the matter and energy of creation were squeezed into an infinitely small space, a beginning. But that was a thought for another era, another generation of cosmologists to grapple with. For now, in the 1920s, the revelation was simply this: the universe had a history. It was not infinite in time, it was not static, and humanity, for the first time, had begun to read the story of its own existence, written across the night sky, in the patient light of distant galaxies and the precise measurements of patient astronomers. There was something almost tender about this discovery, if you stop to think about it. Here was a fundamental law of reality, playing itself out on the vastest scales imaginable, and it could be expressed so simply that a child might understand it. Farther away means faster moving away. That was all. That was everything. The cosmos had been waiting for us to ask the right question, and when we finally did, it had answered with clarity and grace. The question, of course, was why. Why was the universe expanding? What force or principle governed this endless, patient stretching? Hubble himself did not propose an answer. He had done what a scientist does. He had observed, measured, and reported what he found. The interpretation, the deeper meaning, would require another leap of thought, another mind approaching the problem from a different angle, armed with a different set of tools. When Hubble's measurements began to show this curious relationship, this pattern suggesting the universe was not static but flowing outward, the theoretical physicists of the world faced a profound reckoning. And at the center of that reckoning stood Albert Einstein, a man whose own equations had predicted something rather unexpected, something he would spend years trying to undo. You see, Einstein's general theory of relativity, published in 1916, was a revolution in how we understand gravity itself. It did not describe gravity as a force pulling objects downward, as Newton had imagined, but rather as the geometry of space and time itself, the way that massive objects warp and curve the fabric of the cosmos around them, and how all other matter and light must follow those curves. It was elegant, beautiful, and mathematically precise, but when Einstein applied these equations to the universe as a whole, treating the cosmos itself as the subject, he encountered a troubling conclusion. The universe could not be static. The equations suggested it should either expand or contract, but certainly not remain fixed in place. This disturbed him deeply. At the time, the prevailing view among astronomers was that the universe was indeed static, unchanging, eternal in its stillness. It seemed obvious, even common sense. How could everything be rushing outward, and toward what? Einstein believed the observations of his contemporaries, and he trusted the philosophical appeal of a static cosmos, so he did something that would haunt him for the rest of his life. He introduced into his equations a small mathematical term, a fudge factor, if you will, designed to balance out the mathematics and restore stasis. He called it the cosmological constant. The cosmological constant was Einstein's attempt to make the mathematics behave. It represented a kind of repulsive force, an anti-gravity if you imagine it that way, a pressure throughout the cosmos that could push against the inward collapse his equations otherwise predicted. By introducing this term with just the right value, the equations yielded a static, unchanging universe. Problem solved, or so he thought. But here is where the story takes on an almost melancholic tone. As observational evidence accumulated through the 1920s and 1930s, as Hubble's measurements grew more precise, as the reality of an expanding universe became undeniable, Einstein came to see his cosmological constant not as a brilliant insight, but as a grave error. He had let his philosophical preconceptions override what the mathematics was truly telling him. He had not trusted his own elegant theory. When the expansion of the universe became accepted fact, the cosmological constant seemed unnecessary, even embarrassing. Einstein came to refer to it as his greatest blunder, a phrase that would echo through cosmology for decades. There is something almost human in this story, is there not? Here was one of the greatest minds in the history of physics, a man who had reshaped our understanding of reality itself, and yet he second-guessed his own equations because the implications seemed too strange, too counterintuitive. He had been wrong not because his mathematics was flawed, but because he had chosen to override it with an assumption about how the universe ought to be. It is a reminder that even genius is not immune to the pull of convention, to the weight of expectations about what the world should be, rather than what it actually is. And so, as the mid-20th century unfolded, physicists abandoned the cosmological constant entirely. It was left on the shelf, discarded, filed away as a historical curiosity. a monument to a moment when even Einstein had faltered. The universe, it now seemed clear, was dynamic. It was not static, it was expanding, had been expanding since some distant beginning, and this expansion was fundamental to its nature. The static universe model, the old comfortable idea that the cosmos was eternal and unchanging, dissolved like starlight, fading into a dawn that would never come. The acceptance of this expanding universe was, in many ways, a surrender of the older cosmological worldview. It meant accepting that the universe had a history, a past when it was different than it is now, a future when it would be different still. It meant abandoning the notion that we live in a timeless, steady-state cosmos. Instead, the universe became a story, a narrative unfolding across billions of years, with a beginning hidden somewhere in its past. What happened next unfolded not as a dramatic eureka, but as a slow, almost reluctant acceptance, the way a room gradually admits that the sun has truly set, even when we've grown attached to the fading light. For centuries, perhaps millennia, the cosmos had been imagined as a finished thing, perfect, static, eternal, the heavens above, unchanging and serene, a kind of cosmic clockwork that had always been wound and would always tick along in precisely the same way. It was comforting, that idea. It suggested stability. A universe that changed, that expanded or contracted, that had a beginning or might have an end, felt somehow dangerous to contemplate. But the measurements were there now, accumulating quietly in observatories and in the patient calculations of astronomers who had learned to read the universe's written confession in shifting light. Hubble had shown that the farther away a galaxy lay, the faster it was receding. The relationship was clean, mathematical, undeniable. And yet for some time, the scientific community hesitated. Could there be some other explanation, some trick of dust or distance or misunderstanding that might preserve the old vision? Einstein himself, recall, had resisted the idea so strongly that he had introduced his cosmological constant into the equations of general relativity, that fudge factor designed specifically to hold the universe still. When Hubble's evidence became impossible to dismiss, Einstein acknowledged his error, though the full weight of that acknowledgement would not become clear for many decades. He had imposed a kind of mathematical brake on the cosmos, simply because he could not imagine it doing anything else. The universe, it seemed, had been far less committed to standing still than humanity's greatest minds had assumed. The shift in thinking was profound but unhurried. Papers appeared. Conversations continued in the quiet corridors of institutes. The static universe model, the idea that we inhabited a cosmos eternal and unchanging, began to recede itself, like those distant galaxies, and in its place arose something stranger, more dynamic, more alive. The universe was not a sculpture already complete. It was something more akin to music still being composed, space-time itself expanding, stretching, creating new room for itself as it grew. What does it mean, one might wonder in those drowsy moments between waking and sleep, to live in a cosmos that is fundamentally not static? For nearly all of human history, the stars had represented constancy. They moved in their patterns, yes, but those patterns repeated, eternally. The pole star stayed put. The constellations wheeled overhead in their familiar configurations. There was comfort in that rhythm, that sense of a cosmos holding its shape. But now, suddenly, it became clear that everything, absolutely everything, was in motion. The very fabric in which galaxies swam was itself expanding. Nothing remained in one place, because place itself was being created. The implications took time to sink in, truly sink in, beyond the mathematics and into the deeper understanding. If the universe was expanding now, then one could trace that expansion backward through time, rewind it, follow those galaxies as they grew closer and closer to one another. Follow the universe as it grew denser, hotter, smaller. Trace it backward far enough, and you arrived at a state utterly different from anything we could directly observe. A moment of infinite density, infinite temperature, the very beginning of space-time itself. The Big Bang was not something anyone had set out to discover. It emerged logically from accepting that the universe was not static, that it was dynamic, that it had a history. This was both a tremendous intellectual liberation and a strange kind of vertigo. The cosmos was no longer a finished gallery to be observed and catalogued. It was a process, an unfolding, a becoming. Every moment, the universe was larger than it had been a moment before. Every moment, the distance between galaxies increased. The light from distant objects took longer to reach us because the space it had to traverse was itself actively growing. It was as if the universe, in its expansion, was also creating the very stage upon which it acted. The old guard of physics and astronomy had to grapple with this. Some adjusted their thinking with grace and intellectual curiosity. Others held out longer, preferring the elegance of the static model even in the face of mounting evidence. But the data were relentless. Observation after observation confirmed it. The universe was expanding. This was not a temporary condition. This was not a localized phenomenon. This was the fundamental state of reality, the way things actually were, the very nature of existence itself. And perhaps the most remarkable thing was how quickly, in cosmic and human terms, this realization became not shocking, but simply the baseline of modern cosmology. Within a few decades, the expanding universe went from a radical idea to a settled fact, woven into the standard understanding of how reality worked. We built theories upon it. We understood other phenomena through its lens. We came to see all of cosmic history as a story of this ongoing expansion, each moment stretching space a little further, each moment pulling galaxies a little farther apart. There was a gentleness to this acceptance, paradoxically, for while the idea of an expanding universe might seem chaotic or unsettling, in practice it was deeply stabilizing. It provided a framework. It allowed us to ask coherent questions about the past and the future. It suggested that the universe had rules, that those rules could be discovered and understood, that nothing was arbitrary or unknowable. The cosmos was not a mystery in the sense of being incomprehensible. It was a mystery in the sense of being vast and layered, waiting to be explored, revealing its secrets to patient observation and careful thought. And so the static universe, for all its intellectual comfort, gave way to something far richer, a universe in motion, a cosmos with a history, a reality in which time and space and change and growth were woven into the very fabric of existence itself. In letting go of the old model, humanity had not lost certainty, but had instead gained something more profound, the ability to actually understand how things were, rather than how they wished things to be. If galaxies were simply flying away from us like debris scattered by an explosion, then the universe would have a center, the point where that explosion happened, and from that center, everything would be rushing outward into empty space that was already there, waiting to be filled. But this was not quite right. This was the old way of thinking about it, and it took decades for astronomers and physicists alike to reshape their intuition around something far stranger and more beautiful. The key to understanding what is truly happening rests on a subtle but profound distinction. The universe is not expanding into space. Space itself, the very fabric that contains all distance, all direction, all geometry, is expanding. And because space is expanding, galaxies that are woven into the texture of that space are being carried apart from one another, not because they are moving through space, but because the space between them is growing. There is no center. There is no edge. There is no external void into which the cosmos is expanding. Imagine, if you will, the entire universe as the surface of a balloon, not the three-dimensional universe we inhabit, but imagine for a moment that all of space itself is represented by that two-dimensional rubber surface. Now paint dots on that balloon to represent galaxies, scattered randomly across its expanse. When you inflate the balloon, each dot moves away from every other dot. The dots themselves do not crawl across the rubber. Rather, the rubber itself stretches, and the dots travel apart because they are embedded in that stretching material. If you were a small creature living on that balloon's surface, you would observe all the other dots moving away from you in all directions. You would see no special center. Every observer on every dot would see the same thing, a universe of galaxies receding. The mathematics of this expanding balloon and the mathematics of our expanding universe are remarkably similar. This is what the Big Bang truly describes. It is not an explosion of matter bursting into existence at a single point and then spreading through pre-existing space. Instead, it is the beginning of space-time itself. Space-time, the unified fabric that weaves together space and time, emerged and began to expand from an incomprehensibly dense and hot initial state. At that moment of beginning, perhaps 13.8 billion years ago, there was no before to speak of, because time itself was emerging. There was no outside from which to observe the expansion, because space was beginning to expand. In those first fractions of a second, the universe was unimaginably hot and dense. Every particle of matter and energy was crammed into a volume infinitely small, or so the early mathematics suggested, though modern refinements to the theory have tempered that infinity somewhat. As space-time expanded, it cooled. In those first moments, expansion was ferocious. Subatomic particles existed as free and wild forms of energy. There were no atoms, no stars, no galaxies yet. There was only radiation, pure energy, and a handful of fundamental particles beginning to condense from that heat. This is perhaps the most disorienting aspect of the Big Bang to hold in one's mind. The universe did not have a point of origin that you could locate on a map. It did not have a center from which all things rushed outward. The origin was everywhere and nowhere simultaneously. Every point in space today, including the space where Earth orbits the Sun and where you are listening to these words, was present at that initial singularity. Not literally, not in the sense that all matter and energy was compressed into an infinitely small point in space. Rather, space-time itself was involved in that singularity. Space and time were not genera. The Big Bang, the way objects are inside a box. The Big Bang was the beginning of space and time themselves. And yet, even as space-time expanded, it continued to carry the geometry of the universe with it. The shape of the universe, whether it is flat, or curved like a sphere, or curved in the opposite way, was set very early on. We believe today that the universe is very close to flat, meaning that the large-scale geometry resembles an infinite Euclidean plane rather than the curved surface of a sphere. If the universe is truly flat, it extends infinitely in all directions. It has no boundary, no edge, no place where expansion suddenly stops. There is only more universe, and more beyond that, forever, all of it stretching, all of it growing. As expansion proceeded through the first second after the Big Bang, the temperature of space-time dropped below the threshold at which particles could transform into one another freely. Quarks froze into protons and neutrons. These nucleons began to capture electrons and form the first atoms, mostly hydrogen and helium, with trace amounts of lithium. The universe was still opaque, still filled with radiation, still too hot for light to travel freely. But the fundamental building blocks of all future structure had been laid down. When you consider that we can observe galaxies billions of light years away, and that light has been traveling toward us for billions of years, you are looking backward through time itself. You are seeing the universe as it was when it was younger and denser and hotter. And yet, even those ancient galaxies that we observe through our telescopes are not at the edge of the Big Bang. They did not form at the moment of cosmic origin. They arose only after hundreds of millions of years of expansion and cooling had taken place, when gravity had gathered enough hydrogen and helium to ignite the first stars, and when those stars had burned out and scattered their ashes to seed the formation of galaxies. So when we speak of the Big Bang, we are speaking of the beginning of expansion itself, the beginning of the stretching of space-time that continues to this very moment, that continues even as you breathe and listen. The distant galaxies that redshift away from us are not flying through space that was already there. They are being carried on the expansion of space itself, like leaves drifting on the surface of a river. The river itself is flowing, and the leaves have no choice but to drift. There is no still water at the edge of the river, no bank toward which they are traveling. There is only more river, more expansion, more distance being born from the geometry of space-time itself as it evolves and unfolds through time. When the idea of an expanding universe first took hold, one question haunted physicists and astronomers alike. If everything is moving apart, there must be a center. There must be a place from which it all began, some cosmic heart from which galaxies radiate outward like ripples in a pond. Yet Hubble's measurements told a different story, one that seemed to contradict common sense, and for that very reason, it offers us a gateway into understanding how the universe actually works. Imagine, if you will, a ball of bread dough studded with raisins, placed in a warm oven. As the yeast works its invisible chemistry, the entire mass of dough begins to rise and swell. Every raisin moves away from every other raisin. The distance between any two raisins grows larger as the dough expands around them. Now, here is the crucial part. There is no special raisin at the center. There is no privileged point from which all others are receding. If you were a tiny creature living on one raisin, you would see all the neighboring raisins moving away. If you existed on a different raisin, you would observe the exact same thing, the universe expanding in all directions around you. You would never find the center, because the center is not located anywhere. The center is everywhere and nowhere simultaneously, a paradox that dissolves the moment you understand that space itself is expanding. This metaphor, while humble and imperfect, captures something essential about the cosmos. The expansion does not happen within space. Rather, space itself, the invisible stage on which all of existence plays out, is stretching, growing, increasing. The galaxies are not pushing through an empty void like ships sailing outward across an ocean. They are sitting still, in a sense, while the fabric of reality grows between them. Distance itself is increasing. Consider another image, a balloon painted with dots of ink, each dot representing a galaxy or cluster of galaxies. As you slowly inflate the balloon, every single dot moves away from every other dot. The surface of the balloon expands. The distances between all the dots grow. Yet there is still no center on the balloon's surface. No dot is more central than any other. If you were an observer on one dot, looking outward across the balloon's curvature, you would see all the other dots receding from you at speeds proportional to their distance, precisely what Hubble measured. And if you could somehow visit a different dot, you would find yourself at the center of an identical expanding view, with the same mathematical relationships governing what you observe. What makes this metaphor so useful is that it helps us escape the intuitive trap of imagining the Big Bang as an explosion occurring at a point in space. For centuries, when humans witnessed an explosion, gunpowder igniting, a star bursting in the night, it always happened in a place. There was a location where the event began. Our minds were trained to think this way, but the Big Bang was not an explosion in space. It was the beginning of space itself. There was no void waiting to be filled, no empty arena into which the universe erupted. There was no before, no time preceding it. The Big Bang happened everywhere at once, because everywhere, the entire cosmos and every dimension within it came into being together in that singular, inexplicable moment. This shift in understanding required humanity to overturn centuries of geometric intuition. We are creatures who evolved on the surface of a sphere, Earth, moving through a three-dimensional space we can walk and run and jump through. We developed mathematics built on the assumption that space is flat, infinite, and unchanging. Hubble's observations, combined with Einstein's mathematics, revealed something far stranger, that space is not a static container. It is dynamic. It breathes. It stretches. It was born, and it is still being born, moment by moment, in the stretching that continues even now. The raisins in the dough, the dots on the balloon, these images work because they let us think about expansion as a geometric phenomenon rather than a violent event. The universe is not hurtling apart. It is gently, relentlessly swelling. And because every region of space participates in this expansion, every observer, no matter where they stand in the cosmos, experiences themselves as stationary while everything else recedes. This is not illusion. This is as real as it gets. This is what the mathematics tells us is true. There is something almost restful in this realization. The expansion is not chaotic. It is not random. It follows precise laws. The farther away a galaxy is, the faster it moves away. Not because it is fleeing some central point, but because there is more space between you and that galaxy, and all of that space is stretching. It is as though the universe is breathing, and we are living inside the breath, expanding along with everything around us, never knowing we are moving, because we ourselves are part of the motion. And so, as the 20th century deepened, cosmologists found themselves in possession of a strange new picture of reality, a universe that had not always been stretched as it is now, but had begun in some hot, dense point of infinite compression, then unfurled like light itself learning to move. Yet there remained a problem that gnawed at the edges of their understanding, a prediction that seemed almost too elegant to be true. If the universe had indeed erupted outward from such a beginning, then somewhere, woven into the very fabric of space, should linger an echo, a whisper, a faint, cold glow of radiation left behind from those first, ferocious moments when the cosmos was so hot and bright that matter and light existed as one indivisible sea. This radiation would have cooled over billions of years as space expanded around it, stretching the wavelengths of those ancient photons into longer and longer forms, pushing them down from the visible spectrum into the infrared, and then further still into the microwave range, invisible to any human eye, but potentially detectable by the right instruments, tuned to the right frequency. The prediction had been made by physicists in the mid-1960s. It was a bold extrapolation from theory, a test that would either confirm or shatter the Big Bang model entirely. And yet, as often happens in science, the discovery of this cosmic microwave background arrived not through some grand, purposeful experiment, but through what might charitably be called an accident, or more precisely, through the patient frustration of two engineers who kept finding static in their antenna when they should have found none. In 1964, at Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson were working with a large, horn-shaped receiving antenna. Their task was prosaic: to measure radio signals bouncing off ECHO, an early communications satellite. The antenna was sensitive, carefully designed, cooled to near absolute zero to minimize electronic noise. Yet no matter what they did, no matter how meticulously they adjusted their equipment, they detected a persistent, low-level hum of radiation coming from every direction in the sky. It was about 3 times stronger than the theoretical background noise their equipment should have produced. They checked their cables, they cleaned their instruments, they even found pigeons nesting inside the antenna horn, their droppings accumulating on the reflective surfaces, and so they gently evicted the birds, thinking perhaps that was the culprit. The noise remained. Meanwhile, not far away at Princeton University, a team of physicists led by Robert Dicke had been preparing an experiment to detect precisely this cosmic microwave background, the very radiation the Big Bang theory predicted should still be present today. Dicke and his colleagues understood what Penzias and Wilson had stumbled upon, and Dicke, in a moment of grace and scientific generosity, invited them to collaborate on the interpretation. The mysterious hum in their antenna was not an imperfection to be eliminated. It was the voice of the universe itself, speaking from 13.5 billion years ago. This radiation had been released when the cosmos was roughly 380,000 years old. At the moment, matter had cooled enough to become transparent. Before that point, the early universe had been opaque, filled with a blazing soup of electrons and photons, too hot for atoms to form. But as expansion proceeded, as space stretched and cooled, a threshold was crossed. Electrons began to combine with nuclei, forming the first neutral atoms, primarily hydrogen and helium. Light, suddenly freed from its constant scattering by charged particles, was able to travel unimpeded for the first time. The universe became transparent, and in that moment, a vast tide of radiation, the afterglow of the Big Bang itself, began its long journey across the cosmos. Since then, that ancient light has been traveling outward in all directions, its wavelengths continuously stretched by the expanding universe. The radiation that was once scorching hot, with a temperature of roughly 3000 Kelvin, had cooled to about 2.5 kelvins by the late 20th century, just a whisper above absolute zero. When you convert that temperature into wavelengths, you find that this ancient light now occupies the microwave portion of the electromagnetic spectrum, the very same range used by modern communication satellites and microwave ovens. The universe, in a sense, had hidden its birth certificate in the most mundane of frequencies, waiting patiently for human technology to catch up and read it. The discovery was so perfectly aligned with theoretical prediction that it immediately became one of the most convincing pieces of evidence for the Big Bang model. Yet what Penzias and Wilson could measure was only the broad outlines. The radiation appeared almost uniform in all directions, isotropic in the language of physics. But this uniformity created its own puzzle. If the background radiation was truly uniform, then matter should have been uniformly distributed in the early universe, spread evenly like a smooth fog. Yet we know that matter became clumpy. It gathered into galaxies, which gathered into galaxy clusters, which wove themselves into vast filaments spanning billions of light years. How had the smooth universe given rise to all this structure? Later observations, made with increasingly sensitive instruments, revealed that the uniformity was not quite perfect. There were tiny, gentle variations in the temperature of the cosmic microwave background, ripples in the radiation, only 1 part in 100,000 different from the overall glow. These minuscule temperature fluctuations corresponded to regions of slightly higher and slightly lower density in the early universe. In the beginning, gravity had amplified these tiny asymmetries over cosmic time, drawing matter together into the galaxies and clusters we observe today. The cosmic microwave background had, in essence, been imprinted with the seeds of all future structure. What we were seeing was not merely the afterglow of creation, but a fossil record of the universe's infancy, preserved in microwave light for those patient enough to listen. And so the pigeon-filled antenna at Bell Labs had captured something profound, a message older than any human language, older than any stone, older than the earth itself. In the static that Penzias and Wilson had been so puzzled to find was the echo of the universe's first moments, cooled and stretched and rendered nearly invisible by the passage of billions of years, yet still present, still speaking, still teaching us about where we came from and how the cosmos learned to become itself. And yet there remains something altogether stranger, something that happened so early in the universe's life that we can scarcely comprehend the timescales involved. In those first infinitesimal fractions of a second after the Big Bang itself, we're speaking now not of milliseconds but of something so brief it makes a nanosecond seem like an eternity. There may have occurred something called inflation, a period of expansion so violent, so impossibly rapid, that it makes even the ongoing expansion we've been discussing seem almost leisurely by comparison. Imagine, if you will, the entire observable universe at a size smaller than an atom, and then imagine it doubling in size, and doubling again, and again, thousands upon thousands of doublings in a time so brief that light itself could barely traverse the inflating region. This is what inflation theory proposes. It wasn't a steady expansion, but rather a kind of explosive stretching, as if space-time itself had been heated to an unimaginable temperature and suddenly, violently expanded in on itself. In less than a trillionth of a second, the theory suggests, the universe could have inflated from subatomic scales to something large enough to contain everything we see today. The peculiar thing about inflation is that we arrived at it not through direct observation, but through a problem. By the 1970s and early 1980s, when cosmologists had begun mapping the universe with more precision, they noticed something troubling about the Big Bang model as it stood. The universe appeared far too uniform, too smooth, too perfectly balanced. When you looked at different regions of space, separated by vast distances, regions that should never have been in contact with one another, never shared heat or energy or any way to equalize their properties, they nonetheless seemed to have nearly identical temperatures. How could that be? How could such distant corners of reality know anything about one another? Alan Guth, a physicist working at MIT, proposed in 1980 that if the early universe had undergone an extraordinarily rapid expansion, it would explain this uniformity. Before inflation, all of space would have been close enough, hot enough, and connected enough to reach a kind of equilibrium, to smooth itself out. Then, inflation would have stretched this tiny, already uniform region to cosmic scales, making it appear uniform to us now, even though its distant corners are separated by billions of light-years. It's rather like inflating a balloon that's already been painted with perfectly even color. The paint remains even as the surface expands to enormous sizes. And what drove this inflation? That remains one of the great mysteries. The theory suggests some kind of field, called the inflaton field, permeated the very young universe and possessed an enormous amount of energy. As this field relaxed and decayed, releasing that energy, it drove the expansion. But what is this field precisely? What is its nature? These are questions that remain largely theoretical, largely speculative. We have no direct way of observing the inflaton. We cannot recreate the conditions of the early universe in any laboratory. We can only infer its existence from the ways its effects might echo through the universe we see today. Yet inflation theory has proven remarkably useful. It explains not just the uniformity of the universe, but also the patterns of variation we observe, subtle fluctuations in the cosmic microwave background that we'll speak of more fully in a moment. It predicts that space-time itself should be geometrically flat, which observations have largely confirmed, and it does so with an elegant simplicity, a kind of explanatory power that has convinced many cosmologists of its correctness, even if direct proof remains elusive. There are other versions of inflation theory you should know: chaotic inflation, new inflation, eternal inflation, which suggests that inflation might never truly have ended in many regions of the multiverse, if the multiverse is real, which is itself a theoretical notion. Some physicists propose that our Big Bang itself was preceded by a period of cosmic contraction, a bounce, an eternal cycle of expansion and contraction. Others wonder if quantum fluctuations in an earlier era might have given rise to our universe spontaneously, with no prior cause at all. These are the frontiers of cosmological thought, where observation becomes scarce and theory must dance with imagination. The honest truth is that inflation remains partially theoretical. We cannot travel back to that first fraction of a second. We cannot peer into those extreme conditions. We can only construct mathematical models and see which ones seem to match what we observe in the modern universe. And many of them do. But there is always a chance, always a possibility, that future observations might reveal something unexpected, might require us to revise or replace inflation theory entirely. Science, after all, is not a collection of final answers, but rather a conversation with nature, and nature is far from finished speaking. Yet what inflation gives us is a framework, a way of understanding how a universe that began in such extreme conditions could settle into the relative calm and order we perceive today. It suggests that the very fabric of reality underwent a kind of metamorphosis in those unimaginably early moments, and that this metamorphosis was not gentle, but rather tumultuous, chaotic, governed by forces and energies we can barely comprehend. And then, as suddenly as it began, inflation ceased. The inflaton field decayed. The universe's expansion rate dropped from that incomprehensible violence to a slower, steadier pace, and the universe began its long, patient cooling and structuring, its journey from a seething sea of energy toward the galaxies, stars, and worlds we know today. Through the second half of the 20th century, astronomers faced a peculiar challenge that would transform our understanding of how the universe was actually arranged. They had confirmed that galaxies were indeed moving apart, that the cosmos was stretching, but they knew almost nothing about the deeper architecture of that expansion. Were galaxies scattered randomly throughout space, like specks of dust in an infinite room, or did they cluster together in ways that suggested some deeper organizing principle? The work began quietly, methodically, with astronomers spending countless nights at telescopes in places like Palomar Mountain in California and observatories around the world, recording the positions and velocities of thousands upon thousands of galaxies. Each observation was a small step, a coordinate added to a slowly forming map. The process was deliberate and sometimes tedious, yet there was something deeply purposeful about it, a gathering of data that would eventually reveal patterns no one had quite anticipated. By the 1980s and into the 1990s, as computers became more powerful and automated surveys could scan the sky more efficiently, the three-dimensional picture began to emerge with remarkable clarity. What astronomers found was not randomness at all. Instead, they discovered that galaxies were arranged in a vast cosmic web, a structure of almost bewildering intricacy. Galaxies clustered together into groups and clusters, and these clusters arranged themselves along filaments, long, thread-like structures that wound through space like an enormous neural network. These filaments formed the walls of something even more striking: immense voids, regions of space that contained almost no galaxies at all, bubbles of emptiness that stretched for hundreds of millions of light-years across. Imagine, if you will, the structure not as a solid distribution, but as something closer to foam or the cells of a honeycomb, material concentrated along the boundaries, vast hollow spaces in between. A galaxy residing in the middle of one of these cosmic voids would look out and see almost nothing for billions of light years in every direction, a profound isolation that might seem melancholic if we allowed ourselves to project such feelings onto distant objects. But within the filaments and clusters, galaxies crowded together in glittering abundance, held by gravity's invisible threads, moving together in ways that reflected the universe's deep gravitational architecture. This revelation was important for several reasons that might not be immediately obvious. If the universe had been uniformly distributed, the expansion would have felt almost featureless, a simple stretching without character. But because the expansion occurred against this intricate backdrop of structure, it meant that on the largest scales, the universe was performing something like a cosmic inflation of a pre-existing pattern. The voids grew larger, the filaments stretched and thinned. The clusters that once might have been close neighbors found themselves separated by ever greater distances, and yet they remained connected, woven together by gravity's patient holding. These surveys also revealed something quieter, but perhaps more profound, that the universe, despite its unimaginable size, showed a kind of homogeneity on the very largest scales. Zoom out far enough, look at structures spanning billions of light years, and the distribution began to smooth out again. One region looked roughly like another. The lumps and bumps of the cosmic web were real and intricate, yet they were scattered throughout space in a way that suggested the universe was, at its core, relatively uniform. This observation would become critical to cosmological thinking. It meant that you could describe the expansion in general terms, that there were universal rules governing how space itself was stretching, even if locally, in our neighborhood, the pattern was complex and varied. The mapping of galaxies continued to accelerate through the 1990s and into the 21st century. Surveys like the Sloan Digital Sky Survey recorded the positions and velocities of hundreds of thousands, then millions of galaxies, building a census of the nearby universe with unprecedented precision. Each new image added texture to the map, revealed structures on scales that had previously been invisible, deepened the sense of wonder at just how intricate the universe's large-scale architecture truly was. There was something almost meditative about the work, a quality that might have resonated with the observers themselves, though they likely experienced it as scientific labor. Night after night, data point after data point, the universe revealed its pattern in incremental stages, and as the picture became clearer, as the cosmic web came into focus with greater and greater detail, astronomers began to ask a new set of questions. If the universe had these structures, if it had a texture and a pattern, what did that imply about its history? How had such intricacy arisen from what was presumably a more uniform state in the distant past? And perhaps most compellingly, what mysterious influence was governing the overall expansion? For by the time these vast surveys were underway, another discovery was rippling through cosmology, something that would rewrite the story of the universe's future in the most unexpected way. For decades, astronomers had grown comfortable with the expanding universe. The mathematics worked, the observations confirmed it, and so there developed, among those who study the cosmos, a particular kind of question that occupied their evenings at the telescope. Not whether the universe was expanding, but rather how quickly that expansion would slow down and eventually perhaps reverse itself. The gravity of all the matter in existence, they reasoned, must be pulling back against the outward rush. Somewhere in the distant future, perhaps trillions of years hence, the universe might pause in its expansion and begin to contract, collapsing back inward in what some called the Big Crunch. It was a comforting kind of finitude, a story with an ending, and in 1998 that story was quietly shattered. There were two teams, working nearly in parallel, each hunting for the same quarry in the sky. They were searching for distant supernovae, the brilliant, violent deaths of stars, so bright that for a brief moment one of them could outshine an entire galaxy. These stellar explosions had become, in the hands of observational astronomers, a kind of cosmic measuring stick. If you could find a supernova far enough away and measure how bright it appeared from Earth, you could calculate its true distance. The dimmer it looked relative to how bright it actually was, the farther away it had to be. And if you could map the distances to supernovae scattered throughout the universe at many different times in cosmic history, you could sketch out the expansion timeline itself. Had the expansion slowed over the eons, as gravity would suggest, or had it remained constant? These were the questions that drove the two competing surveys. The Supernova Cosmology Project, led by Saul Perlmutter at Berkeley, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, spent months and years peering through the darkness. They used some of the most powerful telescopes then available. They developed new techniques to identify these distant explosions and extract their light for analysis. They were patient, they were meticulous, and as the data accumulated, plotted on graph after graph, a strange and unexpected pattern began to emerge. The expansion wasn't slowing down at all. In fact, it appeared to be speeding up. The very distant supernovae, the ones that had exploded when the universe was younger and distances were smaller, appeared dimmer than the calculations predicted they ought to be. If the universe had been expanding more slowly back then, due to gravitational braking, those distant explosions should have appeared brighter than the nearby ones, because the universe hadn't stretched as far in the interim. But the opposite seemed to be true. The distant supernovae were dimmer, which could only mean one thing. The universe had been expanding more slowly in the past, and was now accelerating. Something was pushing the cosmos apart, working against gravity, doing so more forcefully as time went on. Something invisible, something that filled all of space. Something for which no one had a name or an explanation. The realization spread through the community of cosmologists like a slow shock. Here were two independent teams, using different telescopes, different methods, different samples of supernovae, arriving at the same impossible conclusion. This was not an error. This was not a fluke. This was reality, presenting itself in a way that nobody had anticipated. One of the team members, upon seeing the first hints of this acceleration, reportedly felt physically ill. The comfort of a decelerating, eventually reversing universe evaporated. The future suddenly seemed open-ended again, infinite. And the past, well, the past required a whole new kind of cosmic ingredient, one that defied conventional understanding. The papers were published. The findings were presented at conferences, and across observatories from Hawaii to the Atacama Desert to space itself, other astronomers began to ask the same question. Could this really be true? What in the universe could possibly explain this acceleration? And as the years passed, and more data accumulated, and more teams confirmed the unexpected results, a consensus began to solidify. The universe was indeed speeding up. It had been all along, in fact, though nobody had noticed until the light from those distant, ancient supernovae had finally reached Earth to tell their story. It was a discovery that would eventually earn the Nobel Prize in Physics for those who led the surveys. But more than that, it was a discovery that fundamentally altered how we see our place in the cosmos. Because if the universe is accelerating now, then there must be something pushing it, and whatever that something was, it seemed to make up most of the universe by mass energy. The atoms that form stars and planets, and you and me and every galaxy we could see, all of that familiar matter was a minority ingredient. A small, quiet presence in a cosmos dominated by something we did not understand and could not see, a mystery that remains, even now, at the very heart of cosmology, waiting in the darkness for someone to finally unravel its secrets. And so the universe has been expanding ever since that violent beginning, galaxies drifting apart in the great stretching of space-time itself, the distances between them growing steadily, predictably, according to the pattern that Hubble first glimpsed decades ago. The mathematics was elegant. The observations confirmed it. Astronomers had come to accept that we live not in a static cosmos, but in a dynamic one, forever in motion, forever becoming less dense, forever cooling into the future. It seemed, in a way, settled. The universe would expand, slowing gradually under its own gravity, and astronomers could measure that deceleration, could predict, over hundreds of billions of years, what the ultimate fate would be. But then, in the closing years of the 20th century, something strange emerged from the careful study of distant supernovae. Two teams of astronomers, working independently with telescopes scanning the deep sky, were measuring the brightness and distance of these stellar explosions, using them as standard candles to map the universe's expansion back through time. And when they calculated what they found, when they checked their data and checked it again, they discovered something that contradicted everything they expected. The expansion was not slowing. The universe was not being pulled back by gravity. Instead, it was accelerating. Galaxies were flying apart faster now than they had been in the distant past. Something was pushing them outward. Something was counteracting gravity on the grandest scales, overcoming the attraction of billions of galaxies, and somehow driving the cosmos toward an ever-increasing rate of separation. It was, by any measure, a profound surprise. And it raised a question that lingers still, a question that keeps cosmologists awake in their offices late at night, checking instruments, re-examining data. What is this force? What could possibly be accelerating the expansion of everything? The answer that emerged, the best framework we have developed, involves something called dark energy. And dark energy, you should understand, is not a solution in the traditional sense. It is, rather, a name given to a profound mystery. We do not know what it is. We do not know how it works. We have assigned it a label and built mathematical descriptions around it. But those descriptions are, in many ways, placeholders for something we do not yet understand. Think of it this way. Imagine you are observing a phenomenon, watching the universe accelerate outward, and you ask what causes it. The only honest answer is that something is causing it, something with properties that act like a kind of negative pressure, something that fills all of space and exerts a force that pushes rather than pulls. We call this dark energy. It comprises, according to our best measurements, about 68% of all the mass energy in the universe. Everything we can see, stars, galaxies, the light from a billion supernovae, accounts for only about 5%. The rest, 32%, is dark matter, another puzzle, another mystery. But dark energy is the dominant force shaping the fate of the cosmos, and we are still, in a very real sense, groping in the dark to understand it. One possibility that physicists have explored extensively involves something called the cosmological constant, a concept that circles back, in a strange and ironic way, to Einstein and his reluctant modification of general relativity. Perhaps dark energy is simply inherent to space itself. Perhaps empty space is not truly empty, but possesses a kind of energy density, a vacuum energy that is uniform throughout the cosmos, unchanging in time, pushing outward with a constant pressure. This idea has mathematical elegance. It fits the observations, and it is, some believe, the most parsimonious explanation we have. Yet it raises its own enormous questions. Where does this vacuum energy come from? Why does it have the particular value it does? Why is it not much, much larger? A possibility that physicists call the cosmological constant problem, and it remains one of the deepest unsolved mysteries in physics. There are other proposals, though. Other frameworks that cosmologists are quietly exploring. Perhaps dark energy is not constant but evolves over time. Perhaps it is something called quintessence, a kind of dynamic field that permeates all of space and varies from place to place and moment to moment. Perhaps the acceleration we observe is not due to a mysterious energy at all, but to something fundamental about gravity itself on the largest scales, a breakdown of general relativity when dealing with the entire universe. Perhaps we are misinterpreting the data somehow, though countless careful observations make this seem unlikely. The truth is that we do not know. We have observations, we have a working mathematical model, but we lack understanding. We lack a deep theory that would make sense of why the universe accelerates, why it behaves as it does. And this is important to hold in mind, to sit with as you drift further into thought. Much of what drives modern cosmology remains speculative. We are building models, testing them against data, refining our understanding day by day. But the universe is under no obligation to match our intuitions or our mathematical hopes. Dark energy might be something we will understand deeply in decades to come. It might be something that remains forever beyond our reach, a fundamental limit to human knowledge. It might be something so strange, so far outside the categories of physics we have developed, that we will need entirely new ways of thinking, entirely new conceptual frameworks, before we can truly grasp what it is. For now it remains, as all deep mysteries do, an open space in our understanding, a place where observation meets the limits of knowledge, where the universe invites our wondering and our care. And that is enough. That is, in its way, beautiful. The universe, we now understand, is not slowing toward stillness. It is accelerating outward, driven by a force we can measure but barely comprehend. And yet, even as we observe this endless stretching, a deeper question settles quietly into the mind. Where does this lead? What becomes of everything when time itself has stretched so far that moments feel like eternities? There are several paths the cosmos might follow, each one a kind of ending, though none of them resembles a catastrophic collapse or violent rupture. Instead, they unfold with the same patient, implacable rhythm that has defined the universe since the first moments after the Big Bang. These are not futures to fear. They are simply what comes next, the natural consequences of the expansion we have set in motion, playing out across timescales that dwarf human comprehension so thoroughly that worry itself becomes almost quaint. The most commonly imagined scenario is sometimes called the heat death of the universe, though that phrase carries a poetic melancholy that may be misleading. What it describes is actually a state of almost perfect uniformity and equilibrium. Imagine the universe billions of trillions of years from now, or perhaps even longer. By then, nearly every star will have exhausted its fuel. The massive ones will have collapsed into black holes or scattered their matter across space. The smaller ones, the red dwarfs that outlast everything else, will eventually fizzle into cold, dark embers. Planets will drift untethered through the void. The galaxies themselves will drift so far apart that observers in one galaxy might never know another exists. But the universe would not be entirely empty or utterly cold. There would be a thin fog of radiation, the lingering heat from all that ancient starlight, spread so diffusely across such an incomprehensibly vast volume that no meaningful temperature could be assigned to it. Stars, planets, life itself, all of those would be gone, but the universe would still exist, still be expanding, still be obeying the laws of physics. It would simply be a universe of profound solitude and stillness, a cosmos where time continues, but nothing of significance happens within it. Some physicists call this the final state, though the word final carries a weight that may not be quite appropriate, since time would technically continue forever, even if nothing occurs within it. Yet there is another possibility, less often discussed but equally plausible, and that is one in which the universe continues expanding for eternity without quite reaching such absolute uniformity. If quantum effects and various theoretical particles behave as some models suggest, the universe might never achieve true equilibrium. Instead, it might settle into a state of incredibly slow activity, where rare and improbable events still occur, where entropy still increases but at an almost imperceptible pace. Structures might occasionally form by pure chance, only to dissolve again over timescales so vast that calling them time feels like a courtesy to language. There is also, worth mentioning, though it remains highly speculative, the possibility of the Big Rip, though this requires certain forms of dark energy to behave more violently than observations currently suggest. If dark energy's strength were to increase over cosmic time, rather than remain constant, it might someday overcome all other forces, eventually tearing apart not just galaxies and stars, but atoms themselves. But nothing in our current data points strongly toward this outcome. It remains a mathematical possibility rather than a likely future. The universe is not about to tear itself apart, not for a very, very long time. What might strike you as you contemplate these scenarios is how much uncertainty still lingers in the midst of all this careful calculation. We have mapped the expansion, we have measured dark energy's influence, and yet the universe continues to harbor mysteries. What dark energy actually is remains perhaps the deepest question in physics. We know what it does, but not what it is. We know its gravitational signature, but not its nature. Will it remain constant across billions of years, or might it shift in ways we cannot yet foresee? These are not gaps in knowledge that produce anxiety, but rather the gentle reminders that the universe is larger than any single moment of understanding. Science progresses, understanding deepens, and yet the cosmos always seems to keep something in reserve, some quiet secret held at the edge of what we can know. Consider also that these distant futures are so remote, so utterly separated from the present moment by time spans so great that they exist almost outside the realm of human concern. The expansion of the universe will not affect your life or the lives of anyone you know, or anyone they know, or anyone alive for the next trillion years. The universe has given us billions of years of fruitful existence already. Galaxies collide and merge, stars ignite and burn out. New worlds form and become habitable, perhaps. The expansion continues, yes, but at a pace so gentle that it is imperceptible on any human scale. And perhaps there is something almost comforting in the knowledge that the universe, for all its vastness and its mysteries, plays out according to laws that are knowable. It does not collapse unexpectedly. It does not behave capriciously. Instead, it follows the mathematics that physicists have written down, equations that describe gravity and space-time and quantum behavior. These equations lead to certain conclusions about the future, conclusions we can explore and understand, even if that future is so distant as to be truly irrelevant to the present moment. The universe expands. It will expand for longer than it has already existed. Eventually, perhaps, it will reach a state of profound stillness and uniformity, or perhaps it will continue in a state of rare, improbable fluctuation forever. But these are not catastrophes. They are simply the destination toward which the cosmos has been heading all along, the natural result of initial conditions set 10 billion, 14 billion years ago in the instant of the Big Bang. What remains is now. The stars that light your night sky tonight are the product of that expansion. The atoms in your body were forged in stellar furnaces billions of years ago and scattered by cosmic processes into configurations that became alive. You are made of stellar material, arranged in such a way that you can contemplate the universe's deep future. That alone might be reason enough to rest easy under that expanding sky. And so, having traveled through more than a century of discovery, through photographic plates and patient measurements, through the mathematics of space-time and the whispers of ancient light itself, we find ourselves returning where we began, to that same night sky, that same moment of standing beneath the stars and wondering what they mean, what they are telling us, what they have always been telling us in their slow and patient language. The universe is stretching. This is no longer a mystery or a conjecture debated in quiet observatories. It is simply what the cosmos does. It expands without end, pulling galaxies farther and farther apart, stretching the very fabric of space itself, like an invisible hand drawing a cloth taut across an endless table. And yet, this expansion is not violent or frantic, or even particularly swift when measured against the scale of human experience. It unfolds across billions of years. It is the slowest motion imaginable, so slow that to our senses and to our instruments it seems almost like stillness, almost like peace. When you step outside on a clear night, the starlight that touches your eye has traveled unimaginable distances. It has crossed valleys of space that dwarf comprehension. It has passed through the cosmic web, through the dark voids where almost nothing dwells, and it has arrived at your pupil as a tiny vibration of energy. Some of that light left its source before humanity existed. Some of it began its journey when our species was young and newly learning to look upward and wonder. And in the time it took to reach you, the universe itself grew larger. The distance between that star and your eye increased not because the star moved away from you particularly fast, but because space itself was stretching, stretching, stretching with a patience that belongs to no human measure. There is something profoundly quieting about this realization, something that settles into your bones like warmth. You are standing on a small, warm world. This world orbits an ordinary star in an ordinary galaxy, among billions upon billions of galaxies. You are made of ancient star stuff, forged in furnaces that burned billions of years ago. And you are a conscious observer within an expanding cosmos. You are not outside of this story, you are inside it. You are a part of the universe learning about itself, measuring itself, wondering about itself in the only way a part of the universe can. The expansion continues around you always. It is happening as you rest. It is happening in the darkness above and all around. Galaxies that are impossibly distant are moving farther away at this very moment, not because they are trying to escape, but because the space between them is being borne continuously, gently, without sound or drama or violence. And in this infinite, slow expansion, there is no center. There is no privileged place. Your small, warm world is as valid, as real, as important to the structure of space-time as any other point within it. You stand nowhere special, and therefore, in a curious way, you stand everywhere. The cosmic microwave background, that ancient light released when the universe was young and hot and dense, continues to wash over you in every moment. It is imperceptible. You cannot feel it. Your instruments can detect it only with great sensitivity, and yet it is there, the universe's memory of its own birth, a gentle reminder that everything was once close together, everything was once unified, and then it began to expand, and it has never stopped. Perhaps this is a comfort as you drift towards sleep. The universe is not chaotic or hostile or designed to disturb you. It is simply expanding. It is doing what it has always done, what it may continue to do forever. It is stretching itself into new configurations, creating new space where there was none before, allowing galaxies and stars and living things like you to exist in the room that expansion provides. You are a beneficiary of that expansion. You exist because the universe grew large enough to allow atoms to condense, stars to ignite, worlds to form, and life to begin its slow climb toward consciousness. In the vastness of this cosmos, your worries and concerns take on a different character. They do not vanish. They are real and meaningful to you. But they exist on a scale so small relative to the age of the universe, relative to the distances between galaxies, relative to the expansion that has been unfolding for billions of years, that they find a kind of perspective. They find a place. And that place is valuable, even if it is small, even if it is temporary, even if tomorrow the expansion will continue, and your concerns, while they matter to you, will be held in the gentle context of something far larger and far older and far more patient than any individual life. The questions that cosmologists still ask, that we still cannot fully answer, rest lightly now. What is dark energy really? What came before the Big Bang? Will the expansion continue forever, or will it someday slow and reverse? These remain mysteries. These are the questions that will occupy minds for generations to come. But they are questions that can wait. They are questions that the universe itself does not seem to be in any hurry to answer. And so neither need you be. As you rest, as your mind begins to drift downward into sleep, allow yourself to imagine that night sky. Not the harsh glare of stars seen from a city, but the deep, silent sky known to people far from artificial light. Imagine the Milky Way stretched across your vision like a river of ancient photons. Imagine the depth of space, layer upon layer, expanding continuously into directions you cannot perceive or measure. Imagine the galaxies, each one an island universe, each one filled with billions of stars, each one moving slowly, inexorably away from every other galaxy in this vast, beautiful, patient dance that has no end and no beginning that anyone fully understands. You are warm, you are safe, you are resting in a small place within an infinitely expanding cosmos, and that is enough. That is everything. The universe will continue its expansion whether you are awake or asleep, whether you are thinking about it or not. It will continue with or without your understanding. But for now, for this moment, you have understood something. You have traveled through time and through space, and through the minds of people who looked at photographic plates and saw hints of a universe in motion. You have stood with them in quiet observatories and watched as the cosmos revealed its greatest secret. And now, having reached that understanding, you can let it go. You can let your mind release it gently, the way starlight releases into the darkness, spreading out, thinning, becoming part of the fabric of everything. Sleep now in the knowledge that you are made of the universe. You are the universe experiencing itself. And the universe is expanding, always expanding, toward infinities that have no names, carrying you with it, gently, into the profound and restful darkness.